Introduction, and thanks, Phil, for the invite. Like the introduction said, I'm Joe Cutler. I'm a fifth-year PhD student at UPenn down in Philly, but I'm here in New York for the summer and really excited to give this talk and connect with you all. So I spend most of my time thinking also about, type systems and type theory and various things related to that. But today I'm actually going to be talking about something slightly different. I'm going to be talking about property-based testing, which is sort of a favorite, a favorite side project, a favorite, side hobby of folks in my lab, and I'm really excited to bring this paper to you all. So this project is called Fail Faster. It's about high-performance property-based testing. The title sort of begs two questions. One, for some of you, what is property-based testing? Some of you might know about it. Many of you might not. And two, if you do know about property-based testing, why might we care about making it high performance? What could that even mean? So I want to sort of take this in two parts. And first, for those of you who aren't already familiar with what property-based testing is, or PBT, I want to talk briefly about what PBT is. So property-based testing sort of stands in contrast to the standard example-based unit testing that I very much hope that everybody is familiar with. So in example-based unit testing, I take a function that I'm trying to test, which I've drawn here with this beautiful little red box. I write down a whole bunch of individual input-output pairs for my function. And then I just run the function on each of the inputs, and I check individually that each of the outputs that I wrote down is equal to what you actually get when you run the function on that input. Each successful input-output pair that you write down gives you a little bit more confidence that you wrote your function correctly. And each failure that you find either means that you oops, wrote down the wrong thing for what the function returns, or you found a bug in what your function does. Property-based testing, or PBT, is a generalization of this idea, where instead of writing down individual input-output pairs, you take the function you're trying to test and you write some kind of property about that function, some kind of logical specification that is checkable, that tells you something good about what that program should do. So some nice examples of this are if your function is some kind of addition function, then it should be commutative, probably. Maybe your function is like a serializer, and there's a corresponding deserializer, and the property that you want is that when you compose the serializer and the deserializer, you get the same thing out at the other end. A very common other property that lots of people are familiar with is say your function is a very complicated, highly optimized implementation of a simple idea. The property might be this function behaves identically to a simpler reference implementation. So all of these are examples of properties that I might want to check. And the idea of property-based testing is that you take this property and you feed lots and lots and lots and lots and lots of random inputs through the property from some random data generator, and then you check that the property holds on that particular input. And so each subsequent successful input that passes the property gives you a little bit more confidence that your property is correct. Obviously, you can't most of the time test all of the possible options, but 10,000 is good enough for anybody. And so that's the basic idea of property-based testing. If you get a failing input, it either means that A, you misspecified your program. That's actually an interesting result in and of itself. It means that you're thinking about your program wrong in some way, or it means that you found a bug in your program. Okay? So this is property-based testing in a nutshell. Generate random data, feed it to some executable specification, get feedback. This is a relatively old idea. Property-based testing has been around for around 25 years at this point. It came out of the Haskell community with a library called QuickCheck from a paper from 2001. But since then, it's spread like wildfire to all kinds of different programming languages. And so here's a smattering of randomly chosen programming languages. And each one of these languages has a property-based testing library in it. And I'm sure, I'm willing to bet lots of money on the fact that the programming languages that all of you use on a day-to-day basis has somebody has built a property-based testing library in it. It's relatively simple to do, and lots of people like to do it. So PBT is ubiquitous. It's used plenty in industry. Maybe some of you even use it at your day jobs. One thing that I want to talk about in this talk is that most of these libraries in all of these languages don't actually pay all that much attention to performance. This is a testing framework, right? Why do we care about performance here? And the performance angle is that the faster we can generate inputs, the more inputs that we can throw through this property, the more bugs we can find. Right? I want to try to back this up with a little bit of empirical evidence. So recently, by recently I mean 3 years ago, how the time flies, myself and some collaborators wrote this paper called Property-Based Testing in Practice, where we went out and talked to industrial users of property-based testing to see how they use PBT. And in this paper, we learned that the users that we talked to ran their property-based tests for on the order of 30 seconds tops, right? Property-based testing is not a thing that people do in CI and they leave it to run overnight. PBT is something that you do, you make a little change, you run your PBT, it goes for 10 seconds, then you control-C it, because it probably would have found the bug in about 10 seconds anyways, that's good enough, right? That's not very much time per property. If you have a big suite of properties, that's really not that much time. And so the impetus is on me and my friends, property-based testing library developers, to make sure that if you're giving me 10 seconds of your time, that I'm doing the most that I can with that period of time, okay? So the goal of this paper and this whole project is to improve PBT bug finding just by speeding up random input generation. There are other ways you can think about improving PBT bug finding, but this is the angle we're going to take here. Let's see how fast we can generate inputs. Okay. So here's a quick outline of this talk. 1, how do you actually write these random data generators? 2, what slows them down? Why are they actually, I claim, slower than they could be? And 3, once you've got a faster data generator, does that actually help you find bugs faster? This is going to be sort of an outstanding question that I'm going to defer to the end. But this is the structure of the talk. OK, let's start with part 1. How are random data generators written? So every property-based testing library, going back to the original one, QuickCheck, includes a little DSL, little domain-specific language for defining generators. I'm going to illustrate everything in the rest of this talk using OCaml's base QuickCheck library. This is for 2 reasons. 1, OCaml is the programming language that I use most of the time day to day, and also it's because it's what we use to write the paper. I know that most of you in this audience don't write QuickCheck, don't write OCaml code all the time. That's actually probably healthy. Hopefully, we don't have to see too much particularly complicated code, and if there are any questions about the syntax, I'm happy to field those along the way. We'll keep the amount of code relatively brief. Also, everything that I'm going to say generalizes to basically any other strongly typed garbage collected language out there, which is a lot of them. And I'm happy to talk offline or at the end of the talk about how I talk about in the rest of this, how what I talk about in the rest of this talk translates to your favorite language and your favorite PBT library. But for now, let's stick with OCaml. OK, generators. What's a generator? In OCaml, and basically every PBT library, you get one type, which is an A-gen. An A-gen is a generator of A's, which I've drawn here with this nice little yellow factory box. You should think conceptually of an A-gen, a value of type A-gen, as a box that is inert until I poke it. And when you poke it, it spits out an A. Okay? And then you can poke it again, and it'll spit out another A. And you poke it again, it'll spit out another A, again and again and again. And this is how you feed, a little machine like this is how you feed your property-based tests. Okay. The generator DSL, your PBT library, has a bunch of functions for constructing boxes like this. Let's take a look at some of these functions. One of them is called intgen. Intgen takes a lower bound and an upper bound and gives you back an int generator that every time you poke it, it will give you a value, and that value will be uniformly distributed between the lower and the upper bound inclusive. Okay? So that's how you construct a generator of ints. Right here. Behold, you poke it, it gives you an int. V is uniformly distributed between low and high, let's trust. Of course, you also have return. Return is a function that, given any value of type A, constructs the A generator that every time you poke this generator, it gives you back the value that you passed in. So every time you poke return X, it gives you back the value X. No randomness going on here. And then, oh gosh, that's low down. I hope we can all see this, but it's a complicated OCaml type, so whatever. There's bind, which given an A-gen and a function from A's to B generators, it gives you back a B generator. The basic idea here is that bind GK builds a little generator box that has a copy of the A generator inside of it. And when I poke the bind GK generator, it's going to go and sample from G, which is going to give me an A. And then it's going to construct KA, which is a generator of Bs, and then sample from that once and give you a B. This is the most complicated bit, or second most complicated bit of the talk. But the takeaway that you should take away, if not my beautiful artistic keynote skills, is that bind, this thing here, sequences generators, lets you run one generator and then another generator, where the second generator can depend on the value sampled from the first. Let's take a look at an example to tie this all together. So, oh, that's kind of small. Can we see that in the back? Maybe? Good? Nice. Awesome. Thanks. So, EvenGen is a generator of even numbers between 0 and 200. So this works in such a way that when you sample from it, the first thing that happens is that it's going to draw a number between 0 and 100. That's going to get bound to x. And then that's going to construct the generator, return 2 times that value x. And then we're going to sample once from that. Remember, sampling from the return generator always gives you back the same value. So when you sample from this, it's going to give you some number between 0 and 200. That's an even number. Does that make sense to everybody? Nods? Nods? Good. All up and down nods, no side-to-side nods. Great. Those are shakes. I don't know, whatever. So we're talking about performance. How fast are these anyways? Turns out that one, pretty fast. Okay? EvenGen, the simple one that I showed on the last slide, to generate a single even number between 0 and 200, running that takes about 20 nanos. That's pretty darn quick. But I do want to say that that's because this is a very simple example, and generators of more complicated data take longer to sample each value. Okay? So while this one is a baseline that's relatively low, and we might be a little bit, it might be, oh, how do we even get faster than that? More complicated data does take a lot longer, and we'll see some examples of much slower generators of more interesting things than even integers later. Okay, so how can we make this faster, right? Well, we really just have to kind of approach this like any performance engineering problem, and the only way to make something faster is to tear it apart. We need to understand how generators work. So what is this generator type? Like, what is an A-gen under the hood? In basically every property-based testing library, an A generator, that thing, is just a function type. An A generator is a function from random seed to A. So a generator is just a deterministic function from initial seeds to values. It's a thing that if I give it an initial seed, it will run and then produce a value for me. And so all of the randomness of a generator comes from somebody wiggling the initial seed at the input and getting different values at the output. And so with this definition, we can take a look at how those generator functions were defined. I'm going to go through this relatively quickly because it's dense slides of OCaml. But return is defines the generator that just takes this value, ignores its seed, and always returns it. Right? Conceptually, that's what you would imagine return to do. Bind takes in its seed, runs the first generator, binds that to a value A, calls k on A to construct the next generator, and then samples from it. Right? It's just calling the two one in sequence. Right. And then intgen constructs the generator that when you give it a seed, it samples from what I'm calling R, which is like the underlying random number generator of the DSL. All property-based testing DSLs sort of are built on top of some random number generator. And so all that intgen does is every time you sample from it, it just goes and asks for a random number from the RNG. Okay, so now that we've sort of looked under the hood, and now that we've seen how these generators work, we can use this knowledge to make them faster. And one idea, which is sort of the simplest idea in trying to optimize something, is let's just inline everything in sight and see what happens. Okay? Let's inline and see if we can simplify some things. So we're going to take a step back to our original very simple generator here, EvenGen, and start simplifying. So the first thing to note is that we have this call to return. And the first thing that I'm going to do is I'm just going to inline the definition of return. Right? Recall that return is just the function that takes in a seed and returns the thing that we passed it. So this is seed goes to 2 times x. And then now for the most complicated slide of all, we are going to take the definition of bind, unfold that one step. A whole lot of things just happened. Let's ignore all of the context with the exception of down here. One of the first things that we notice is that here on this line, we have an anonymous function, fun x goes to blah, 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 that immediately is going to get applied to this value here. And if you think about how anonymous functions work, you can just apply that right now. The first thing that's going to happen is this anonymous function is going to get defined, and then it's immediately going to get applied. So we can just reduce it, substituting the variable for the argument in the body, like I was trained in college. Then we have another instance of that again. Right? We have this seed, this function that's immediately applied, and so on and so forth. And we can keep playing this game. I'm going to skip through this because it's not particularly interesting. But we keep playing this game, inlining function definitions, and then when we see these anonymous functions that are immediately applied, just do the application ourselves. And once we're done with that, we end up with this thing. right? That after inlining everything and simplifying away all of the combinator definitions, we get that evengen is the generator that, given a seed, samples from the underlying random number generator a number between 0 and 100 and returns 2 times that number, right? Like, at its base, that is the simplest thing that this should be. So we went from that thing that was defined in terms of return and bind and intgen and these sort of fancy functional abstractions, and we've ended up with just like the simple program. All we've done is just manually unfold the definitions and inlined. What if we benchmark this now? Aha! All we've done is inlined the definitions and done some simplification ourselves, and we've got like a 1.3 repeating x speed up, okay? And that's a shocking speed up for like the fact that there was very little actually going on initially. Like it was a very small program, we've done a little bit to it, and it's gotten 1.3x faster. Pop quiz, why? Anybody have thoughts? Anybody have guesses? Yeah. The question was, isn't your interpreter doing this anyway, so now instead of doing it at runtime, you're doing it at compile time? Sort of, the first thing is that this is a compiled language, so if anything would be happening, it would all be happening at compile time. But the answer is that, yeah, there's something going on where like the compiler isn't doing something that we are doing manually. Does anybody have thoughts about what's actually causing this? Yeah, you in the front.
Well, I was thinking like it's allocating all these like little closures and stuff.
Yeah, bingo. That's the answer. It's allocating all these little closures and stuff. Closure allocation and garbage collection is the answer here. So calling functions like return and bind and all of these nice functional programming abstractions that we like to use, especially doing it lots and lots and lots of times over and over in a very tight loop, generates a lot of garbage closures which need to be cleaned up, right? Using return and bind, etc., uses these little anonymous functions. When you define an anonymous function, it has to go somewhere, and in particular, in OCaml and every programming language like it, that gets heap allocated, right? It gets allocated on the heap. You call it, you run the code, and then you move on. And then eventually, the garbage collector has to come back and sort of clean up all of those closures, all of those anonymous functions that you've created along the way. And that's the overhead here. That takes a shocking amount of time, especially when you're generating, 2.5 million ints as fast as you possibly can. You're going to generate a lot of garbage just of closures, okay? And we'll note that this guy here has much fewer anonymous functions than the original one at the beginning. So there's less garbage being generated. That's basically how it works, okay? So in the biz, people call this abstraction overhead, right? Abstraction overhead is the price that you pay at runtime in the time it takes to run your program for using these nice functional abstractions. So the fact that you get to program with return and bind and all sorts of other higher order functions in your property-based testing library, you lose out at runtime the fact that that takes time to clean up all the garbage that those things generate, okay? The obvious question here is, can we build a property-based testing library without abstraction overhead? Right? It seems like we should be able to do this without having to do all that work. After all, generators are completely statically known. They're totally known at compile time. Your compiler should be able to do the manual thing that we just did together up on the board here entirely automatically. In fact, I think that some of you are probably already thinking this, wait, doesn't my compiler already do that kind of thing? I would be so happy to talk about what compilers do and don't do offline. They do much less than you want them to. And also sometimes things you don't want them to. But in particular, your compiler does not do those transformations. Yes, your compiler does not do those transformations that I just described. But in fact, can we build a PBT generator library without abstraction overhead? Yes, we can, with something that's called multi-stage metaprogramming. I don't have time to talk about exactly what multi-stage metaprogramming is, but multi-stage metaprogramming is a thing that comes from the programming languages literature, sometimes known as staging. And the basic idea is that it's a kind of metaprogramming very similar to macros or templates or things like that, where programs sort of partially evaluate at compile time, inlining away these abstractions that if they were to run at runtime would generate a whole bunch of garbage and incur a runtime cost. Okay. This has been used in the past in the programming languages literature lots and lots of times to eliminate abstraction overheads in DSLs for things like parsing, database queries, linear algebra. There are lots of wonderful papers and blog posts and things you can read about how to speed up a particular kind of DSL by using stage metaprogramming. Let me do a quick time check. Oh, I didn't even start the timer. Well, guess you're all stuck with me. There are a couple of languages that support exactly the thing that I am calling multi-stage metaprogramming, in particular OCaml and Scala and Haskell and F#. F# has it. But you can do similar things in basically any programming language that has like macros or templates or proc macros or things of that nature. Okay. So what we've done in this paper is we've proposed this technique called Allegro. Allegro is, in short, a way of building generator DSLs using staging, this multi-stage metaprogramming, to guarantee that those manual simplifications that we did happen automatically. Okay? It's a way of building your generator DSL so that any generator you write in it has those transformations and some more automatically applied to them so that the thing that actually ends up going to the compiler at the end of the day isn't going to do all sorts of, generate all sorts of garbage. We've actually taken this idea and implemented it twice, once in OCaml and once in Scala, two languages with stage metaprogramming support. The one in OCaml we're calling AllegroCaml, and the one in Scala we're calling Scalegro. Thank you very much. Right. Oh, the other thing to say about these briefly is that these are this is a technical point, but it's interesting. They're sort of pointwise equivalent to their unstaged counterparts. So if you write the same generator in base QuickCheck, the OCaml property-based testing library, and in AllegroCaml, they run identically. They are pointwise equal functions, except that the one in AllegroCaml runs much faster. Same thing with Scala check. Okay. So basically, how this works in practice is that you write what looks approximately like the same generator with a few syntactic annotations that have to do with the way metaprogramming works. You write even gen, and then it becomes, at compile time, automatically, by virtue of using our library, before it even goes to the compiler, all of those abstractions get inlined away, and it becomes the fast thing on the bottom. So you get to write the thing that looks nice, modulo some syntactic cruft, and you get to run the thing that runs fast. Okay. I want to mention that the things that Allegro, or both of the Allegro libraries, do to optimize your property-based testing generators is not just the inlining and simplification that I described earlier. That would be a little bit boring, but because we know that the code that we are optimizing is property-based testing generator code, there are sort of some property-based testing specific optimizations that we're able to do to optimize some common patterns in PBT libraries. I'm happy to talk about the way that those things work offline. There's a whole lot more in the paper. This paper is available on my website, not yet published anywhere. But we do a whole bunch of fancy and interesting staging stuff that we stole from the PL literature to keep that semantic equivalence that I mentioned earlier. We have a long discussion of how and when we think this kind of technique could work in languages other than OCaml and Scala, which is sort of top of mind. OCaml and Scala are cool, but not exactly the greatest languages for widespread industrial impact here. I love them, and I love everybody who uses these things. This is going online. Anyway. And the last thing is there's a whole other half of the paper that I haven't had time to talk about, which is that one thing that really, really matters in property-based testing in terms of generator performance is just which random number generator you choose. It turns out that the speed of your RNG, which is the core of the beating heart of every property-based testing generator, is the RNG, and it really matters how fast it runs. And so we have a couple of some discussion of different RNG techniques and ways that we think you could make RNGs faster, as well as sort of a little performance intervention that we make to an artificially slow random number generator to make it faster, to show what kind of bug finding power you can get. Okay. This is a graph of some generator speedups that we got. Unfortunately, I was not able to regenerate them to actually show you the thing that I care about. So let's just focus on this one here. Also, I didn't realize the room was going to be like long, like narrow and deep. So let me just say this in words. We implemented a bunch of generators for different kinds of data types. So binary search trees, Boolean lists, those are kind of boring. The most interesting generator we implemented is a generator for well-typed, simply typed lambda calculus terms. What that means is well-typed programs in a very simple functional programming language. So it's sort of, this is a very complicated generator. It's hard to generate random well-typed programs in a simple functional programming language. This is, a couple hundred lines of generator code. But the upshot here is that per value sampled, it is across the board about an order of magnitude faster to sample from the staged generator compared to the unstaged generator. So in these generators over here, which are simply typed lambda calculus terms, lists of bools, and binary search trees, you get like a factor of 10 speed up just from the staging in terms of generation time. We do this again. That was all in OCaml. We do this again in Scala. It's actually, you get even better. It's like 1.5 order of magnitude speed up from doing the staging in Scala, because the Scala implementation of the property-based testing library we use actually generates even more garbage than we thought. OK, now for the burning question. Cool, you did all that work. You made generators faster, go Joe, and collaborators. Does it actually find bugs faster? Like, that's cool, you did the performance engineering. Does it find bugs faster? And the answer is yes. Hopefully, you probably want me to back that up. And luckily, some collaborators of mine, not including me, were very forward-thinking on this. So there's this paper from a couple of years ago called Etna. Etna is a tool for evaluating property-based testing generator libraries. So a couple of years ago, some friends were like, I think in the future, we're going to have some different generators, and we're going to want to see which ones find bugs faster. Let's build a framework for doing that. So what Etna is it's a list, it's a bunch of programs, and a bunch of predefined bugs that we can inject into those programs, and then we can sort of have generators race to find those bugs. So we take two generators that we want to see which one is faster, and we just have them race to find these bugs. And it hopefully takes the same amount of time to run the program each time, so that just comes down to how fast it is to generate the data. OK. There's a bunch of graphs that you can find in the paper. I'm again going to skim over this so we can talk about details. The thing you want to look at here is the blue. On a large suite of examples involving of programs involving binary search trees, involving simply typed lambda calculus terms, that simple functional language, we found bugs on average, on geometric average, 2.65 times faster in wall clock time. The actual wall clock times involved are like on the order of 30 seconds. So like we're talking from close to a minute down to 30 seconds in terms of time to find. Some bugs were found relatively quickly, and then they get found even more quickly. Some bugs take a while and are get found in like a little bit less of a while. I will note that like the tails on this go both ways. You never are like really slower than a 2x speed up, and sometimes we find the bugs like 18x faster. About 2 times faster for some binary search tree tests. And then here's our least impressive number, which is that we have this generator called BST repeated insert, which generates binary search trees by generating a big list of numbers and then repeatedly inserting them into a binary tree. Which, if you think about that, that's not particularly bottlenecked by the actual random generation. That's bottlenecked by like inserting the numbers down into the tree. And that's why that doesn't get that much faster when you. So I think that this is actually really important to point out, which is that like our technique works well when there's a complicated generator going on. And if the random generation isn't actually the bottleneck here, then you're not actually going to get all that much improvement, which is kind of what you'd imagine, right? STLC is a very complicated generator. They use a lot of very complicated combinators that generate a whole lot of garbage. And staging it gets you some pretty significant speed-ups in bug finding. OK, that's the talk. Here's my contact info. You can find the paper, the draft of the paper. It's likely to change because we're continuing to revise it and submit it places. But feel free to grab it off my website and take a read. Thanks.
For future questions.
Yeah, we'll do. Yeah.
Did you test your implementation with property-based testing?
Did we test our implementation with property-based testing? You bet we did. Absolutely. So I said that thing earlier, like, hey, the staged generators that you get are sort of pointwise equivalent to the unstaged generators. Guess how we checked that fact? We didn't prove it, we tested it with property-based testing. So if you write down a generator and generate lots of random seeds and then check the equality of the generated outputs, now you can be pretty confident that your generators are equivalent to their unstaged counterparts. That was actually like totally critical in getting that correct. It's very hard to maintain that semantic equivalence through all of these program transformations, and it requires a lot of fiddly, it's very complicated. And having the PBT set up where we could just try to test it, try to run the generator 2 different ways and see if it was the same was like super useful. So I'm a client of PBT as well. Yeah.
I guess I kind of have two. I feel like a lot of the programs we write, we want to assert properties over, use a bunch of complex domain-specific objects, and I would rather not have to write a generator to produce the whole thing. And at least in Rust, I've used some derive arbitrary, and that's nice. How does that fit in here? And then the follow-up is sometimes a thing for which I had liked property-based testing is state machines that have transitions that are due to events, and the events that can happen are relative to the state or to the history of events. How does that fit?
Yeah, so the questions are, number one, often in property-based testing, you don't handwrite the generators, and instead you sort of automatically derive a generator based on a type of some sort. Let me answer that one first. So that totally fits into this schema here, and in fact, it's an even better story for us. So one of the things that's a little bit annoying about using our libraries is that you have to think about the manual annotations that are required to get it to type check with all of the templates. Think about it's not as bad as this, but imagine you had to write your generator in C++ templates. It's not literally this, but think that way. We can, based on a type, automatically generate a staged generator. And you don't have to do any of the work about thinking about how the staging works. It just automatically gets derived. The other first author on this paper, Thea, wrote that implementation, and it's very cool. That's super portable and is a zero cost thing. Okay, question number 2. Often, property-based testing involves testing some kind of state machine where the state machine is responding to events, and the events depend either on the current state of the machine or the past history of events. Yes, we are sort of agnostic to exactly what the generator does here. You can write a generator like that using the staged generator combinators, and it would get faster. Although, again, and this is underlying all of this, this technique, speeding up generation, works best when your tests are bound by the generation time. If you're running tests that take a really long time with simple inputs that are easy to generate, you're not going to get much from this. So it sort of depends on exactly the balance between the complexity of data generation and the length of the time it takes to generate your inputs.
I mean, it is often the case also that the handling of these transitions is extremely fast.
Yes.
So
Yeah, no, that is totally the case.
Generation bounds often.
Sweet. Yes. Yeah, I mean, especially if you're trying to do very clever things, you have a long history of things, and you're trying to generate an event that looks sensible given the history of previous events, and you have to do a lot of logic. The more logic you have in your generator, the more garbage you're going to generate, and the better you're going to do having staged it. Mm-hmm. Yeah.
Is there a succinct explanation you can give about why compilers can't just do this? Because this seems like a broadly useful transformation to be able to apply to any program.
Great. So there's 2 reasons that compilers can't or don't do this. The first one is code size. So inlining increases code size because inlining might duplicate, when you inline a definition, it might duplicate the things that you're inlining to their definition sites. And code size is something you want to be very careful about. And so compilers don't willy-nilly do that. And when you don't inline, you don't expose opportunities for simplification. That's thing one. Thing two is that in lots and lots of languages, like basically with the exception of Haskell, doing inlining naively is not a semantics preserving transformation. You end up reordering effects like printing and random sampling and things like that. And so doing that kind of, in the PL biz we call it beta reduction, where you apply an anonymous function by substituting. That's like not safe in most compilers, and they'd have to implement some kind of purity analysis to make sure that you can do that. I said except for Haskell. None of this is useful in Haskell. GHC, the Glasgow Haskell compiler, is like one of the most impressive pieces of software that has been built in the last 30 years, and I will talk forever about it. But because everything in Haskell is pure, like they can just do all of this without thinking about it. And here's the crazy thing. The reason that all of this, in my opinion, the reason that all of this works in the first place, and that there's so much performance to be squeezed out of property-based testing libraries because they do all of this, they do such inefficient things, is because they're all based on a Haskell library that didn't have to think about this, right? The original quick check library in Haskell, the authors of it knew that they could use all of these functional patterns and they'd get inlined away and it wasn't a big problem. But then as soon as you port a Haskell library to OCaml or Python or JavaScript, oh boy, you have to be very careful if you're trying to think about performance. Like, GHC is like a machine purpose-built for eliminating functional abstractions. Yeah.
And do you still, with this technique, would you squeeze performance out of a non-garbage collected language because of the overhead, the other overhead, basically?
So the question is, how does this apply to non-garbage collected languages? And I think that there would probably still be some effect, especially with some of the optimizations that we do that aren't just inlining and function application. But that particular one, like closure allocation and garbage collection, not a big cost in like Rust or C, right? Like insofar as you're doing property-based testing in C, like Right. The real story is that, like, if you go look at the most popular Rust property-based testing libraries, they don't actually work this way, right? Because you don't actually usually do lots of like higher-order functional programming in Rust. Instead, basically, how you generate random data structures in Rust is like you generate one big template and poke different values into it, and sometimes prune it in different ways. That's how like Bolero and prop test work. Do people know about this? Question mark? Yeah, I'm getting nods. Okay, good. I said the right thing. I'm like not a Rust expert, but I think, yeah.
Yeah, so in that same vein, there's also like an RNG component that you didn't really talk about. Mm-hmm. Is that what would be like the most valuable thing in a language like Rust? Like just optimizing the RNG?
Oh yeah. There is a huge amount. So the question is, in a language like Rust, would optimizing the RNG, would optimizing the RNG be sort of the biggest performance benefit? We don't talk about this a ton, particularly in the paper, because the things I'm about to say don't necessarily hold up to scientific scrutiny. But I am personally of the opinion that there's a ton of low-hanging fruit in optimizing RNG in PBT libraries for languages like Rust, especially because when you're doing property-based testing, you don't care about like statistically significant randomness, you don't care about like secure randomness, and you don't even necessarily care about like real randomness at all. You need a buffer of entropy that you can rip through really fast. You don't need it to be consumed live. You can just pre-allocate a big buffer of entropy and bump a pointer along it reading the values. And that's always going to be cheaper than doing some arithmetic and bit shifting in your RNG. And so like I think that there's a lot of things that you could do in especially a language like Rust to get some super performant RNGs that aren't even like random number generators. They just sort of read some entropy, because all you need is a source of randomishness to read from. Yeah.
Well, while we're on random number generators, you briefly mentioned that you played with a lot of random number generators. Which ones did you like and which ones sucked?
So I did not play with a ton of random number generators. So but I have some thoughts about random number generators. The OCaml-based quick check is based on this RNG called split mix. and the Scala check one is based on, it is XOR in its name, but I can't pronounce it. XOR sure. Yeah, I didn't know how to pronounce it, but that one. Zorshiro is like too complicated to run as fast as we wanted it to. Also, Scala is complicated because it's JITted. Splittable, you don't actually really need splittable random like seeds for most property-based testing. That's an artifact of Haskell. Why that is like so. The original QuickCheck library used a splittable random number generator because Haskell impurity and weirdness, and so for that reason, most property-based testing libraries have just picked up splittable random for that reason, or sorry, split mix for that reason. But you don't actually usually need like the ability to split your state, so you can do other things. The particular thing that we talk, and I have to say this out loud because it's very funny. The particular thing that we do in this paper is that like the OCaml splittable, the OCaml split mix implementation uses like OCaml's strange value representation, which like has like one word allocated 64-bit ints. So like every single arithmetic instruction allocates a word. So that's why it's very expensive in OCaml, which is hilarious. I'm about to be cut off, but yes, sorry, Phil.